I don't know. So for Unit 10, we're totally switching gears and we're working with probability, what we call permutations and combinations. So we're actually going to be looking at different ways, the probability of choosing different things and different ways that you can arrange things is pretty much what we're doing. So we're starting out with an example. A sporting goods store offers 3 types of snowboards. There's all mountain, freestyle, and carving. And there's 2 types of boots, soft and hybrid. How many choices does the store offer for snowboarding equipment? So I already gave you the solution, but let's look at it. What they did was drew a tree diagram for each possibility. If you get an all-mountain ski or snowboard, there are 2 types of boots, soft and hybrid. So that's 1, 2 choices, right? If you have a freestyle board, you can also get soft or hybrid boots. So that is 3 and 4 choices. And if you have a carving board, you can also get soft or hybrid boots. So that is 5 and 6. So how many possibilities are there for your equipment? 6. Now, there are 3 different types of snowboard and 2 different types of boots. What do you guys notice about that? 3 times 2 gives me 6. Okay? That is called the fundamental counting principle. So that's the first definition we have. Okay? The fundamental counting principle tells us that for each number of choices, we multiply those together and that'll give us a new decision. So if we have 3 types of snowboards and 2 types of boots, that means there's 6 different ways that we can combine them, so you have 6 different choices. Okay, so example 1, the store in example 1 also offers 3 different types of bicycles. You can get mountain bikes, racing bikes, or BMX. And 3 different wheel sizes, 20-inch, 22-inch, and 24. How many different bicycle choices does the store offer? 9. We have 3 different bikes times 3 different types of wheels. So there are 9 different combinations or different choices. That's the fundamental counting principle. Make sense? Okay. Let's look at example 2. Now we're looking at license plates. Okay. The standard configuration for a Texas license plate is 1 letter followed by 2 digits followed by 3 letters. Oh, let me change the color. Okay, so we have, and there's an example right here. 1 letter, 2 digits, and then 3 more letters. Okay, question A says, how many different license plates are possible if the letters and digits can be repeated? So notice in my example, I have A for my first letter, and my other 3 letters are also A. 9 is my first number, and my other number is also 9. So we can repeat letters and numbers. So let's look at this. If we have 1 letter, so I'm just going to first write out a letter. Okay, not any letter, L4 letter. After that, we have 2 digits, so that's a number and another number. And then there are 3 more letters. So 1, 2, 3 more letters. Okay. Is that better? Okay. And it's blurry now. Okay. So let's think about how many different options we have here. How many letters do I have to choose from? 26. How many different digits do I have to choose from? 10, right? I have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are 10 digits that I can choose from. If I can repeat letters, how many digits are there to choose from for the second number? 10. Also 10. How about letters? 26, 26, and 26. So what do you think we're going to do with all of these? We're going to multiply all of these together. You can use a calculator. I will give it to you. It is 45,697,600. So if these are the parameters for choosing a license plate, that's how many different license plates we could make. Okay. What about B? Let's look at part B. B asks us how many different license plates are possible if letters and digits cannot be repeated. So this time order actually does matter. So we're set up the same way. We want a letter, a number, and then 3 more letters. Okay. How many letters are there to choose from for the first one? 26. How many numbers? 10. Okay, now I cannot reuse the number that I just used. So now how many numbers are there to choose from? 9. What about letters? 25, 24, and then 23. This is actually going to give me a smaller amount of license plates I can make, right?
Yeah.
It gives me 32,292,000, and that's it. All zeros at the bottom. The difference is that we could repeat letters and numbers in Part A, but in Part B they said we cannot. So after I pick the letter A, I can't use A anymore in my license plate. That's what it means. Okay, so it's still a lot, but not as many as the first time where order doesn't matter. Okay, so we actually, for Part B, we have a special name for this. It's our first definition. It's called a permutation. So a permutation is what Part B of the second example was. When a group of objects or people are arranged in a certain order, the order of the objects is very important. So order does matter for a permutation. So Part B is considered a permutation because the order matters. Okay? So instead of having to write out all of our different possibilities and then multiply it together, you are actually given a formula. Okay? The formula is when given to us for the number of permutations of n objects. So n is how many, for example, different letters we had to choose from, taken r at a time. So sometimes you're going to be given, say, I have 26 letters in the alphabet and I'm picking 3 at a time. How many different permutations are there? So sometimes we will be picking a certain amount at a time, and we'll do an example. So the formula is the permutation of n objects r at a time. There's another way that we could see this. So this could also be written as n objects permutated r times. So you might sometimes see the problem given to you, little n, big P, little r. Okay, so these two are the same thing. Equals n exclamation point over n minus r exclamation point. Does anybody know what the exclamation point means? What does it mean? It is called a factorial, besides being excited. Okay, the exclamation point is called a factorial, so let's label that right now. Okay, and the factorial means that whatever number you are taking the factorial of, you are multiplying that number all the way down to 1. So 6 factorial, that's how we read it, means 6 times 5 times 4 times 3 times 2 times 1, and you multiply all that together. So what would 10 factorial be? 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Your calculator does have a button for that. So we do have a special case. 1 factorial is obviously going to give us 1, but we will also come across 0 factorial. Now 0 factorial is equal to 1. It's a special case, just an identity, something we have to memorize. Okay, so anytime you see 0 factorial, it's just automatically equal to 1. Otherwise, we're always going to get a lot of undefined answers. Okay, so anytime we come across a 0 factorial, it's equal to 1. Okay, so let's look at our first example. Okay, example 3. How many 4-letter patterns can be formed using the letters A, B, C, and D if each letter is used exactly once? So we are taking permutation of, how many letters do we have to choose from? 4. How many are we picking at a time? 4. So that is the permutation of 4 taken 4 times, or we could also write that as 4 permutated 4 times. They are the same thing. Okay, the formula was n factorial. Our n is a 4 here, so that is 4 factorial over.
Is that an exclamation?
It's an exclamation point. Over 4 minus 4, and the factorial of that answer. Okay, so this gives me 4 factorial over, what's 4 minus 4? 0 factorial. So 4 factorial is the same as 4 times 3 times 2 times 1 all over 1. So that gives you an answer of 24. So there are 24 different patterns that you can make if you choose the letters A, B, C, and D, and you can only use them exactly once. And we actually could list them all out on the board if we really wanted to. You would only get a 24 total. Make sense? Yeah? Okay, let's look at example 4. Example 4, how many ways can 3 books be placed on a shelf if they are chosen from a selection of 8 different books? So what's the n in this case?
3.
No, how many do we have to choose?
8.
We can have 8 to choose from. How many do we take at a time?
3.
We can only take 3. So does that make a little bit more sense?
Yeah.
Okay, so this is 8 permutated 3 times, or we can write the permutation of 8 and 3. Okay, so that is n factorial. N is 8. So 8 factorial over 8 minus 3 factorial. You should never get a negative answer as a factorial. Okay, the smallest you could ever get is 0. So this is 8 factorial over 8 minus 3? 5 factorial. Now let's write all of this out first and see what happens. This is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 all over 5 times 4 times 3 times 2 times 1. What can we do before we start multiplying everything together?
Eliminate.
There's a lot of canceling we can do. Those 5s cancel, those 4s cancel, the 3s cancel, 2s and 1s all cancel. So this all comes out to 8 times 7 times 6, which gives me, anybody? 336. I'm only writing it out right now so that you notice that a lot of things are going to end up canceling. In the next set of examples, you don't have to write them all out. Okay? So for example 5, there is actually 7 different problems. I want to do at least number 4, and then I'm going to have you guys do the rest on your own. So this is 5 permutated 3 times. So what I want to do first is I'm going to write it out again. That's 5 factorial over 5 minus 3 factorial, which is 5 factorial over 2 factorial. Now what's going to cancel here? 2 and 1 is going to cancel, so what will I be left with? 5 times 4 times 3, which gives me 60. So there's actually, after we realize that a bunch of stuff is going to cancel, there's a lot less work that we have to do. Okay? You guys okay with that? So will you guys do 5, 6, and 7 by yourself? Okay, so number 5 is 4 permutated 1 time. So that's going to give me 4 factorial over 4 minus 1, which is 3 factorial. So 3, 2, and 1 all cancel, so my answer here is just 4. Okay, number 6 is 8 permutated 5 times, so that's 8 factorial over 8 minus 5 is 3 factorial. So I know that 3, 2, and 1 will cancel. So this is going to be 8 times 7 times 6 times 4, which gives me, times 6 times 5 times 4, thank you, which gives me 6,720. Yes?
Yeah.
Okay.
Wait, for number 5,
Okay, and then the last one is 12 factorial over 12 minus 7 gives me 5 factorial, so that is 5, 4, 3, 2, and 1 all cancel, so that's 12 times 11 times 10 times 9 times 8 times 7 times 6, which gives me 3,991,680, right? Okay, so you actually, all of the work that we did in example 4, you can write all of that out, even if you just show what I wrote in 4 or 5, 6, and 7, that's enough work for me too. Okay, so as long as you recognize that things cancel, you can show this little amount of work. Okay? Makes sense? Okay, so we do have to worry about what happens if there is a repetition. So this happens a lot in the types of problems that example 8 is given as. When the number of permutations n, and we have p objects that are alike, p and q objects that are alike, we have a new formula that we have to plug in. N is going to be the number of choices we have total. How many do we have to choose from? P, Q, and any other numbers are how many times a certain choice is repeated. So that's going to be n factorial over p factorial, q factorial. Okay, let's look at example 8. Okay, I'm giving you the word Georgetown. And I want to know how many different ways the letters can be arranged. Now this is a little bit difficult because I have some repeating letters here, right? Okay, so first let's look at what's my n. How many letters are in that word? 10. So my n is 10. So this is 10 factorial. That's the top part. Okay, so this has 10 letters in there. What letters are being repeated? G is being repeated how many times? Twice. So that is our first repetition. So it's 2 factorial because it's repeated 2 times. Okay, what else is being repeated? E is being repeated how many times? Also twice, so it's times 2 factorial again, because E is repeated twice. And then I see one more that's being repeated. O is being repeated also 2 times, so times 2 factorial again. What if there were 3 O's? It would be times 3 factorial. Okay, so it's not always going to end up as 2, it just ended up that way in this example. Okay, so let's write all of this out. 10 factorial is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 all over 2 factorial is 2 times 1 times 2 times 1 again times 2 factorial again, so another 2 times 1. Do you see anything that cancels? 2 and 1. Anything else? Good. The 2 2's, 2 times 2 gives me what? 4. So we can cancel the 4's with those 2 2's.
Wait.
Yes.
Can't you just make why can't you just make all that 6?
You could multiply it all out and then reduce.
no, that would make 6. That would make 8.
This would make 8.
Oh, 8. No.
Yeah. And we can also cancel out the 1's, right? Because having everything over 1 doesn't change the answer. Okay, so what does this leave me with? This leaves me with 10 times 9 times 8 times 6, 7 times 6 times 5 times 3. That's going to give me 453,600. So I could take all of those letters and rearrange them, and I could get 453,600 different arrangements of those letters.